So I'll begin with a scripture today. Get my phone to work here. So this is Proverbs 26, 4 and 5. It says, do not answer a fool according to his folly, or you will also be like him. And then verse 5, answer a fool as his folly deserves, that he not be wise in his own eyes. So I know it's kind of, these are good verses to live by these days. There's a lot of foolishness in our world. So anyway, I'll begin with a word of prayer. Heavenly Father, we thank you for this day again. I thank you for this class and for this opportunity we have to study your creation. Just pray that you guide our steps today. Help us to glorify you, what we do, Lord. In my prayer, Lord Jesus. Amen. So I know we have some, I don't think you're in my class. Okay, good. All right. And you're not in my class. Okay, good. Okay, good. It's always embarrassing when I identify one person in the class as a CFAR who's actually not. Wait a minute. My eyes aren't very good. In the back, are you? In the middle? Are you in the class? Okay, good. Okay, phew. It's kind of dicey because I can't really see that far. Very good. So, but I try not to identify my students as visitors, if at all possible. Okay, so we have covered differentiation and all the differentiation rules and techniques, and I hope you've learned them. I do have a minute for homework question if you guys have a homework question. Anybody? What's that? 204. All right. 204, these are the logarithmic differentiations. All right, I guess I can never get enough logarithmic differentiation. Which part, A, B, C, or D, or E?
We'll go with A.
You can go with A?
Yes.
I think we did that one in class yesterday, though. Yeah. We did that one in class yesterday as well.
Which one did we not do?
I feel like we didn't do, well, we did C in class. Did we do, maybe, I'm trying to think, did we do B? I'm pretty sure we haven't done D. I'll do 204D for you. 204 part D, let's look at that together. So here we have y equals to e to the minus x squared. All right, the square root of x plus 3 divided by 3 to the power x. And we're supposed to differentiate this using logarithmic differentiation, all right? So, what's our first move? Our first move is to take the natural log of it. So if we do that, we have the natural log of y is equal to, I'll write out a step here because sometimes you guys get stuck on this one. In fact, let me just write out the steps. I'm not going to use my my Uber lemma that we had the other day. And again, it's totally fine if you guys can immediately go to what I'm about to write, which is minus x squared plus 1/2 natural log of x plus 3 minus x log 3. So that's the point. The whole point of the logarithmic differentiation idea is to convert a product and a quotient to a sum and a difference, because it's way, way easier to differentiate sums and differences than it is to differentiate quotients and products. And now we'll differentiate implicitly, right? So differentiate with respect to x. What? Oh, okay. Yeah, I just got a bunch of lousy markers today. Sorry. If I hit the table just right, it dribbles into the trash can, but it's kind of an art I haven't yet learned. All right, 1 over y, dy dx by the chain rule. And we differentiate over there, we get what? Minus 2x plus 1 over twice x plus 3. And then minus, well, log 3. And now, finishing move, solve for dy dx. And we get minus 2x plus 1 over 2 times x plus 3 minus the natural log of 3 all times y. But what was y? Y was that mess up there. So e to the minus x squared square root of x plus 3 divided by 3 to the power x. There you go. So that's problem 204D, which is amongst your many homework problems, yes. Other questions? Maybe one more question, if there's one more question. Okay, well, I'm going to go on then. Cool. So we are in now chapter 4 of my notes, right, which is on derivatives and linear approximations. So, so basically we're talking today about linear approximations. And so, you know, if somebody asks you, well, what's the point of the derivative? A good answer to that is, well, the point of the derivative is to give the best linear approximation to a function near a given point, all right? And so here's the definition. If f is function with f differentiable at x equals to a, all right, then the linearization of f at a is, here's my notation, L sub f upper A of x is by definition equal to f of a plus f prime of a times x minus a. All right. That's the definition of linearization. So if I ask you to find the linearization of a function, I'm asking you to do this. So before I do much more, can you guys tell me what this is? Anybody? Like, what if I was to write say, y equals to LFA of x? What would that be? I am my own cameraman. It's kind of okay. But the people at home get what they pay for, you know? My channel's not monetized. If you CFARers want to see what we've been doing the rest of the semester, you're welcome to go to my my YouTube. I got a YouTube channel, James Cook, like James Cook Math or something. You can find. I record pretty much everything I teach here, so that gives you a pretty wide cross section of the math major and the engineering service courses, at least as I've taught them. Anyway, so what is this, guys? Can you tell me? If I write this, does it help? What is y equals to a line which goes through the point a comma a, f of a, and has slope f prime of a? What is this? Yes, the tangent line. Right, this is the tangent line. So the best linear approximation to the function is the tangent line. So in other words, the linearization, another way to say this, is the linearization is nothing more than the function whose graph is the tangent line. All right, that's it. So let's look at an example. Let's work on, how would you calculate the square root of 4.01 via linearization? So to make this make most sense, you have to, first of all, imagine that the calculators are evil. at least the ones that are connected to the internet for sure. You can imagine yourself in the robot holocaust, whatever it takes, But we need to do calculation without the help of computers. Although I will be using my calculator slightly to help me with this example. I realize the hypocrisy in this. But this one has no Wi-Fi connectivity, so it's safe. All right, so just saying. So which function should I look at maybe? How about this? I should think about f of x equals to the square root of x with maybe a equals to what? What's close to 4.01? 4, right? And that's a good choice because we know that in that case, well, let's see here, f prime of x is equal to 1 over 2 times the square root of x, right? And so we can calculate what is f of 4 is the square root of 4, which is 2, and f prime of 4 is 1 over 2 times the square root of 4, also known as 1 over 4, right? Actually, maybe I can survive this example without getting my calculator out. I don't know. So what would be the linearization of f? Let's see here at the at 4 of 4.01. What would that be equal to? So we'd be looking at. My bad. Let me just write down the formula first. Of x is equal to 2 plus 1/4 x minus 4, right? There you go. That's the formula. This is the formula for the linearization of the function. Now let's use it. Let's use it. So if we calculate the linearization of 4.01, we would have 2 plus 1/4 of 4.01 minus 4, right? Which is like 2 plus 0.25 times 0.01, right? So in other words, this motivates the approximation. The square root of 4.01 is approximately 2 point what? How does this multiply? Do you guys remember how this works? I know it's been a minute. You're like, we've been using calculators since like grade 3. So what are you asking us? Yeah, point what? 2.0025, right? Now, you can compare that, right? You can compare that to the calculator answer and see how we did, as the calculator is currently not evil, right? So let's see here. So that is versus my calculator, which tells me 2.002498 and then stuff. But so let's see here. So as you can see, we are actually successful in all the digits we gave, right? We actually got the square root of 4.01 all the way out to here, didn't we? If you round up that digit, we did that well, right? Let's take this out for a spin. Let's do something ridiculous. Let's calculate the let's calculate the square root of 5 with this formula. So like, what's the linearization of f at 5, right? So in other words, we've got 2 plus 1/4 of 5 minus 4, right? Which would be what? 2 plus 0.25, yeah? Which is what? 2.25. Versus, what's the calculator tell us the square root of 5 is? Well, actually, it's not too crazy. Square root of 5 is actually about 2.2361. So how many digits did where were we accurate in our approximation this time? Looks like just these two, right? From the calculator. Now let's be really ridiculous. Let's try this for something that we won't need the calculator for, but it's just illustrative of the pattern. Let's try it for 9, okay? So the linearization at 9 would be 2 plus 1/4. I'm always just going back to this formula here, guys, right? 2 plus 1/4 of 9 minus 4, which of course is 2 plus 1/4 of, what's that, 5. So we get 3.25 versus the actual answer, which of course is 3, right? So it looks like it's getting worse. Why is this? Like, let's understand this graphically. What's the graph of the square root function look like? Yeah, we're getting farther. So we're always on the tangent line using the linearization, right? Because that's what it is. But if I were to graph this at 4, we're about like here, right? And so what's going on is as you go further and further out, right? You get a worse and worse approximation. And of course, when we're really close to the limits of my artistry, you really can't tell the difference, right? So this is one thing we can use derivatives for. We can set up linear approximations to functions. And so that's a very useful idea because it's much easier to analyze a line than it is to analyze something that's curved, right? Another good example of this that you use in physics a lot, example 2, you might think about f of theta equal to sine theta, right? And then f prime of theta is what? Cosine, right? Right? So what's the linearization of f at 0? It would be f of 0 plus f prime of 0 times theta minus 0, right? But what is that formula actually? Well, sine of 0 is 0, right? Cosine of 0 is 1. So this just becomes theta. So the linearization formula essentially becomes just sine of theta is approximately theta. So this is what the linearization tells us. This is good for theta close enough to 0. Yeah. And what else does this assume? Let's try this out. Sine of 30 degrees, right, is equal to 30. But wait a minute. Sine of 30 degrees is equal to what? What's sine of 30? I was looking for a half, but yeah, you guys are fine. So this is 1/2, right? I mean, sine of 30 is 1/2, correct? Trigonometry. Is 1/2 equal to 30? Well, obviously not, right? So this is nonsense. On the other hand, you guys just told me sine of pi over 6. Well, that's kind of okay. What's pi over 6 equal to? I'll have to use my evil, well, not yet evil calculator. Where'd I put it? Oh, duh. Good job. All right, so what we got here is pi divided by 6. That gives me, so saying that's pi over 6 approximately. Well, pi over 6 approximately is 0.524-ish. All right? So, well, actually, that's not too shabby, right? Because sine of pi over 6 is actually 1/2, which is 0.5. So if you analyze this more carefully, which is a little bit beyond the course in terms of where we are at the moment, all right? But this is something you could prove in calculus too. You could show that sine of theta is equal to theta to within, let's say 1% for basically minus 20 degrees less. So, see, I know it in terms of, this is annoying. I know the approximation's legitimacy in terms of degree, but I really want to write it in terms of radian here. So let's see here. I got to convert 20 degrees to pi to radians. How do I do that? 20 divided by 180 multiplied by pi. Okay, so pi, about roughly speaking, minus pi over 9 less than theta less than pi over 9. Basically in that domain, sine of theta is equal to theta to within about 1%. You get past that, you get larger and larger errors, but yeah. So linearization, of course, is an important idea. But the idea of linearization is, in a nutshell, simply this: replace a function with its tangent line. Right? Now, this is actually just the first step in a much larger idea, which is to replace a function with a better polynomial approximation. Like if you can replace a function with its tangent line, you could just as well replace it with like the best quadratic approximation or the best cubic approximation. But that we don't do until later, a little bit later in this course. And I only do that in this course because I'm misbehaving. Technically speaking, that's really calculus 2 and something called Taylor's theorem. But it is something we should talk about in this course, and I will, and you'll be tested on it, so don't misconstrue my comments. But I don't test too deeply on it either, as only someone as crazy as me would actually talk about it here. So anyway, best linear approximation is the starting point. Now the other thing you can do is talk about the differential. Differential at x equals to a. So here we talk about dy is equal to f prime of a times dx. But what this is actually implemented in as is typically the change in y is equal to f prime of a times the change in x. So this is the so-called method of differentials as it applies here. This principle is that the change in y near a can be approximated by the derivative times the change in x. And it's almost the definition of the derivative, really. The way this is used in applications to science and engineering, for example, like error analysis. The place you might use this would be some kind of error analysis. So let me show you. Example 3. So like suppose you have a cube, all right? You have a cube, and you know that the cube has a width of 10 feet, right? And it got a depth of 10 feet, and it's got a height of 10 feet. It's a cube, all right? So in this case, the volume would be equal to x cubed, right? And it just so happens that x is equal to what? 10 feet, right? Now you say, well, that has nothing to do with the differential yet, all right? Now imagine that you knew that this measurement of 10 feet, it's a physical measurement, right? So every physical measurement comes with some uncertainty. Yeah? Can you measure exactly 10 feet? Well, you might be like, I've got a laser measurer and it says that it's accurate to it. Well, I mean, we do have some pretty neat toys these days, but if you just have a regular, let's say, tape measure, and you measure something 10 feet, what's the uncertainty, do you think? What would be a reasonable amount to say? 1/10 of an inch? Sure. So 10 feet plus or minus, say, 0.1 inches. Now that's annoying because you've given me something not in feet. So I need to say delta x is something like, 0.1 inches. Let me convert that to feet. How do you do that? How many inches in a foot? 12. So let's see, I got to do 0.1 divided by 12. That is 1/120th. 1/120th of a foot. Or let me put that in decimal form. 0.0083, and I'll just keep that much, okay? So a way to kind of express this mathematically would be this. We could say what we have is that x is equal to 10 feet plus or minus really 0.0083 feet, okay? So that's an uncertainty. A natural question to ask in view of this is, what's the uncertainty in the volume? If that's the uncertainty in the length measurement, what's the uncertainty then in the calculated volume? The differential gives an answer to that. It says that the change in the volume is equal to, what's the derivative of 3x squared? Excuse me, what's the derivative of, good grief, what's wrong with me? What's the derivative of x cubed? Yeah, I kind of spoiled it, didn't I? So 3x squared delta x. Now this is a general idea, all right? In the specific application that I have here in this example, we would look at what? Our change in volume, our uncertainty in the volume would be like 3 times, what was my x? Well, 10 feet, right? 10 feet squared times what? Times my delta x, which is about 0.0083 feet. All right? So what is my uncertainty in the volume of the cube here? So I got to do 3 times 10 squared, also known as 100, times 0.008. And those 3's are repeated if you want to repeat them, but I'll just do that. So it actually works out to 2.49 cubic feet. So an uncertainty of just 1/10 of an inch, right, in your measurement, length measurement, results in an uncertainty of about 2.5 cubic feet for a cube like that. So calculus can help us to understand how a little change in some physical variables results in a corresponding change for variables which are dependent on those variables. That's another use of the derivative. All right. All right. So next, I want to explain to you guys what is Newton's method. So let's get to that, if I can. You guys ever heard of Newton's method before? Yes. So high school calculus, or? So how would you explain what Newton's method is if I was to ask you? Just another way to approximate? That's a good answer. Yep. It has a lot to do with what I'm erasing, right? So let me walk you guys through the idea of Newton's method. It's all about linearization. So Newton's method, the problem that we're given is we've got some equation we want to solve. All right? And let's characterize the equation in terms of a function. Right? So we've got some function, and essentially we're looking for what's called a root of the function. All right? A root. So a root of the function is a specific number that you can plug into the formula for the function and get back 0. So our goal is this, is solve f of x equals to 0. All right? That's the goal of Newton's method. Why is it called Newton's method? What's that? Probably developed by Newton. That would be correct. Although, in all honesty, I bet other people knew about it before him. I mean, there were bits and pieces of calculus that were known to the people that came right before Newton. I think I told you guys before, I mean, there were ancient mathematicians who knew calculus. They just didn't have a language which ordinary folks could understand. But anyway, so let's, just for the sake of theoretical understanding, let us begin with a function. Let me see here. I don't know if that's going to be Yeah, that should probably be okay. I don't know. I don't know. I'm going to try and then I'll regret it. Okay, so here's a graph y equals f of x, theoretically, okay? We want to solve this. So the first thing you have to do is make a guess. Newton's method starts with a guess. All right, so I'm going to just illustrate the guess by saying my initial guess is going to be like right about here, just because I'm dumb. Not because I'm dumb, because I want the graph to be interesting, okay? So, all the way I'm dumb. So f of x naught, we're going to call y naught. Y naught. So that gives me this point right here, right? And then what we'll do is we'll look at the linearization based at that point. So the linearization based at that point, something like this, all right? And so here, this is y equals to the linearization of f. Let me just write the formula. It's y is equal to y naught plus f prime of x naught times x minus x naught. Right? That's the formula. That's the formula for the linearization based at x naught. Do you guys see that? So this is the linearization of f based at x naught. Y equals to that, okay? The formula for it's there. So I hope I haven't. Well, we're going to try it. So as you can see, it will intersect somewhere, right? It's going to intersect some point. Like here is where that intersects. And so Newton's method says to approximate the function, you replace it with the tangent line. So if you want to find the zero of the function, you should look for the zero of the tangent line. Maybe that gets closer, right? Now this one didn't work very well, did it? It's actually taken us further away from the way the zero actually is. So I hope this doesn't go badly for me. But that's going to give us this as my next tangent line, okay? So this point here would be x1 comma y1, right? Now y1 would be f of x1. What's x1 equal to? x1 is what you get from solving the red equation equal to 0. So if we take y naught plus f prime of x naught times x, we'd have x1 minus x naught is equal to 0. That defines x1. It's the value which puts us to 0 for the red tangent line. Solve that for x1, what do you get? If you solve this for x1, what you get is x naught plus, I feel like that might be wrong. Yeah, no, not plus, minus x naught minus y naught divided by f prime of x naught. Like, just work it out, okay? So f prime of x naught times x1 minus x naught is equal to minus y naught, and then I divide by f prime. And then I add x naught to the other side, okay? That's x1. All right? So there's a formula for x1. Then what? We look at the tangent line of this. Like that, all right? Oh man, I have illustrated how Newton's method can fail. Good job. So we are going to fix this graph to make things work out more nicely for me. We are going to make this guy bend up a little bit more, like this. There, in the interest of this lecture actually having an end. Otherwise, I'm just going to be Newton's methoding out into the wall over there. That wouldn't be good. Anyway, so I'm trying to here. So with the adjustment, sorry, poor planning on my part, we have the second tangent line based at x1, right? So here we're looking at y equals to LF of x1 at x. And so this was x1 here. And this will be x2. How do we find x2? Well, to find x2, we're looking for 0 is equal to LF x1 when you plug in x2. So when we work that out, we'll find by the same algebra we just did that x2 is equal to x1 minus y1 divided by f prime of x1. Because the role of x1 and x2 is the same as the role of x0 and x1. And that will give me another tangent line. I'm going to run out of colors here pretty soon, so I think I can only go to about 3 iterations. But so on the graph, we have x down here. We've got the point, y2. And then I can look at the tangent line to that, right? And that, for my graph, is pretty much already at the solution to the limits of my artistry. All right? And to find the x3 here, x3 would be equal to x2 minus y2 divided by f prime of x2. So what we're looking at here is actually called an iterative method. So the iterative method goes like this. The n plus 1th step in Newton's method is equal to the nth step minus y from the nth step divided by the derivative at the nth value, like this. So it's an iterative method. So I might ask you a token question in the homework about this. And sometimes I ask like a theoretical question about it, but I don't actually tend to ask you to actually implement this on a test because it's not that interesting. It's just gory arithmetic. This is how computers solve problems. This kind of iterative method. In fact, most of numerical methods on a computer are either Newton's method or that Taylor's theorem I was talking about a second ago. But any questions? Let me show you on the projector an actual one with numbers in it, because I think I have one, if we still have time. Yeah, we got time. Because there's something else I should talk to you guys a little bit about. So we've talked a bit about functions being differentiable, but there's an issue called continuous differentiability we hadn't talked about yet, and I should at least mention that in passing before we get too far away from it, so let me do that. But first, let's look at Newton's method, if I can find it. Well, I will eventually find it. So, yeah, one of the things that made Newton able to do what he did is that these kind of calculations we're doing right now, you can start to appreciate how deeply rooted they are in the decimal expansion, aren't they? Like if you don't have decimal expansions of numbers, these things we're talking about today become exceedingly worse to think through. If all you had was rational numbers, fractions, it'd be really, really hard to carry out analysis. But the real numbers in their decimal form were really only invented about maybe 50 years before Newton came on the scene. So the kind of detailed decimal number-based calculation that Newton was able to do is in large part thanks to his moment in history. Let's see here. All right, so again, Newton's method is make a guess, see where the value of the function is at the guess. If your initial guess almost gives you 0 to the accuracy you're interested in, you're done, right? Otherwise, you calculate the tangent line at that point and you look for where that intersects the origin. That defines x1 as we calculated. And then you calculate f of x1. If f of x1 is close enough to 0, you stop. Otherwise, you go on, find the tangent line at x1 and look for where that crosses the origin. that gives you x2. And then you calculate f of x2. If it's close enough to 0, then you stop. All right? So you see that's the algorithm. All right? By the way, if you take Dr. Wang's numerical methods class here, he probably explains to you guys some, there are ways of making this algorithm a little bit more sophisticated. If you, instead of using the derivative at the point, if you use the maximum value for the derivative on the domain of consideration, then you can be assured that the iteration will converge at a certain rate. You can put a bound on the error at any given step. So there are more sophisticated versions of this thing that a numerical methods person would know. And I can tell you where to look them up, but I am not a numerical methods person, but I do care about it a little bit. But anyway, so the formula for the n plus 1th term, you take the nth x and you subtract the value of the function divided by the derivative, right? By the way, this method fails if what? If f prime of xn is what? 0. That's part of what was wrong with my example over here, right? The fact that there was a place where the derivative is 0 is exactly what was getting us into trouble over here. Because if I'd followed that, it would have actually put my guess way over here. If I'd actually take that point of tangency and follow the tangent line to where it has a 0, its 0 is way, 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 way over there. It's that derivative being 0 that ruined things. Anyway, so we do need non-zero derivative for best results. And here is for the function e to the minus x squared. So what I'm doing here actually is I'm solving. So the first order of business in these kind of problems is often to create the function. If we're solving the equation e to the x squared equals to x, what's the function that we're actually interested in? See this? I'm solving e to the minus x squared equals to x. So that's not a function, right? I can't apply Newton's method to that. So I trade that for a function e to the minus x squared minus x. Now, this function having a root is tantamount to that equation having a solution. All right, so that's step number 1. Then step number 2 is to make a guess. So I guessed minus 0.2. All right, this right here is a graph of the function e to the minus x squared minus x. So just to show you how it's working, if I make my initial guess 0.2, then that's a subnaught, I guess. If you can, I can't see it, but that's definitely a 1. So there you go. That brings us over to here. That makes my first iteration over there. Next, I calculate x2, and I get 0.324. And that brings me to over, that makes my x2 is there. And then I look for where the intercept of the x2 tangent line is. That defines x3 as 0.686. And then what I do is I do 0.65. I do the next one. And let's see here. So that's a good question. If you don't know the answer already, how would you know, as a rule of thumb, that you were close to the answer that you don't know? So this is not rigorous, but a reasonably successful method is when you're doing the method, right? If you get the same, you'll start to notice as you're applying this method that you'll get digits which are fixed, right? As you go on, you'll get more and more and more digits repeated in each answer. And so it's, setting aside malevolent examples constructed by evil math professors, the problems you'll find in the real world, you'll see that if going from one iteration to a next, if the digit's repeated, that's probably a certain digit. So with that method here, I think to the approximation that I'm interested in, we have 0.653 as a solution for e to the minus x squared equals to x here. So that's that. So the other thing I wanted to talk to you guys briefly about is, I'm going to go back here a bit, the concept of, and I forgot to talk to you guys about this, but I really should have back here, maybe. Sorry guys, I'll find it eventually. Well, I was just looking at my notes before class and I saw it, so it must be here. Oh, there it is. So there is, so we have proved in here that if a function's differentiable, it's necessarily continuous, right? We're talking about the function though. If the function has a derivative, that means that the function is differentiable, excuse me, continuous. However, there is no guarantee that just because you can calculate a derivative of a given function, that that derivative function has to be continuous. This right here is an example of a function which is everywhere differentiable. So this f of x is x over 2 plus x squared sine of 1 over x. That's the definition for the function when x is not equal to 0. When x is equal to 0, we just define it to be 0, I believe, all right? And it turns out that you can prove that this function has a derivative at 0. And that derivative is equal to 1/2. That requires like a squeeze theorem argument. I don't want to do it. But it's true. Like the function is differentiable at 0 and the derivative is 1/2. And yet the derivative function, f prime of x, is this. This function is not continuous at 0. So this is a function which is differentiable at 0, but it has a derivative which is discontinuous at 0. This is a function which is said to be, this function is not what is said to be continuously differentiable. To be continuously differentiable means that it has a derivative and the derivative is continuous. These are the nice functions that we like to say most of our theorems about. Here is a graph of the function in red. All right, here is a graph of the derivative function in green. So what it does at 0 is it like that, you know? So what's going on is it's infinitely wiggly at 0, right? And so, you know, you can find quotes from 19th century mathematicians saying this is the sort of thing that gives them nightmares. Like there are literally quotes like this, and this kind of example is one of the things that kept the rigorous foundations of calculus from being fully developed until about 1850. So anyway, I thought I should mention, it's something I never test on, but it is a point of clarification I should mention. So anyway, I hope you guys enjoy your homework. Have a good weekend.
This class is the first math class?
Yeah, this is Calc 1.